circles. Okay, let's get started. So, you have written homework due Wednesday. Sorry, I haven't been keeping up with the reading workbook assignments for Mondays and Wednesdays. I know that's probably been disappointing for you. I've kind of been a zombie the last week, sickness-wise. So we'll get back on track. But let's start today with a review. So I want you to try to recall how would you describe the angle 1.5 radians? So how would you write a statement that explains exactly what that angle is? 1.5 radians is, see if you can remember without looking at what you wrote down. Okay, so let's start off with that. What is the angle 1.5 radians? Take a minute to see if you could construct a good definition. Okay, so trade your ideas with this person next to you. So explain that to the person next to you. Go. Is an angle like that big? Okay, like that?
It's smaller.
Okay, so back to the exercise. How do we know exactly what that angle is? So anyone want to give it a shot in your own words?
That subtends 1.5 radius lengths of a circle.
Whose rays? And what does this word subtend mean?
Cut off.
Yeah, so the rays, if you set the vertex on the center and then you let the rays shoot out, they'll cut off an arc length, right? That's what subtend means. So it's the angle whose rays subtend. What'd you say? I'm sorry.
1.5 radius lengths.
Yeah, right. 1.5 radius lengths of arc length. That's right.
Did you say circumference too?
What's your whole definition? Tell me the whole thing.
Did I say that 1.5 radius is the angle whose radius subtends 1.5 radius on the circumference of the circle?
Or on the circumference. So of is like you're kind of implying percent of the circle. We're not really using that here. We're just saying 1.5 radius lengths on it.
Okay.
So yeah, you could say 1.5 radius lengths on the circumference. Yeah. So if this is one radius length here, this is our one radius length, then about, just estimating here, about where's an arc length of 1.5? Here? More or less? If we want 1.5, we need more. More or less? Still more. Oh no. Dang it. Shouldn't be that hard. Okay, so what about where it is now? No one's commenting. Is it about right? Okay, it's about right. It's close. Right, because if that's one radius length right there, then we're saying it's the angle that would, such that this arc length right here is 1.5 times those. 1.5 times whatever that radius is. Okay. So that's a review of the definition. So when we looked at our nice whole numbers of radius lengths, this was 1. And then starting here at the 3 o'clock position, that was 2. And then 3. And then 4, 5, 6. And we said it was, maybe about 6 1/4 radius lengths to get all the way around. About 6 1/4. Okay? What's the so these are nice values of radians because they're nice whole numbers. But there's a kind of a disadvantage to working with these numbers of radians. What is the disadvantage? Yeah, they don't land in any useful places in terms of symmetry of the circle, right? So what we're interested in is nice places on the circle. For instance, the top of the circle. So from 3 o'clock position, a helpful question would be how many radius lengths or how many radians to get exactly to the top of the circle, or 1/4 of the circle. So to get that, we said that we figured out last time, what is it exactly halfway around? Yeah, that's what this number pi is. You've all heard of that number before. I'm sure you celebrated it over spring break, right? March 14th is Pi Day. It's this infinite decimal. It goes on and on and on. And so we need all the decimal places all the way to infinity. That's what exactly the number of radius lengths to get halfway around the circle. About 3 and another 14% of a radius length gets us exactly halfway. All right. So what about 3.14? Does that get us halfway around? Not quite, right? What about 3.1416? Too far or too short? 3.1416. Too far, a little bit too far. Okay? So you have to have every decimal place all the way to infinity perfectly right, and that will get you exactly halfway around. Well, that's kind of not convenient, right? So that's why we use the symbol pi. Pi represents that exact value with all its decimal places all the way to infinity, so we get exactly an angle that subtends exactly half of the circumference. Okay? So from that, starting with that, we know then a really important thing is exactly how far is it for one full rotation? 2 pi, right? So it's going to be 2 of those. And that's critically important for finding angles as a percent of the circle, right? We need to know what that 100% mark is for radians. 100% is 2 pi. Okay? So the first thing we can do is we can break the circle up into fourths. 1/4 of the circle will be what angle in radians? It can be pi over 2. Okay? So we got 1 pi over 2, 2 pi over 2, 3 pi over 2, or 1.5 pi. So this is 1 pi and then another half pi, right? So that's 3 halves pi. So 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, which is 2 pi. So those are very helpful, important places on the circle in terms of radians. So what would you estimate? Don't use your calculator, but 3 pi over 2. What would you estimate that value to be? And how do you know?
70 degrees.
So what would you estimate the value of 3 pi? So what happens with these is they just become symbols and they lose their meaning. So but this is a number. What number is it about? What's that? Why 4.5? Okay, so you're just trying to do the division,
Pi plus a half a pi.
right? But what's that? 3/4?
Like 3/4 of the circle.
Okay, it is exactly 3/4 of the circle. Yeah, the question I'm asking is really, it's a number of radius lengths, right? And here we know exactly how many radius lengths these values are. So that's what I'm asking you to use to predict what 3 pi over 2 is. What would you say? Four 4.8, do you see? Because this is it's still, even though we're starting to introduce the value, this symbol pi, it's still a number of radius lengths swept from the 3 o'clock position. Just like these were, 1, 2, 3, 4, 5, 6 radius lengths. Just like pi is a little bit more than 3, 3.14. Okay, so now find 3 pi over 2 in your calculator. What'd you get? 4.71? Yeah, just a couple is good. Does it make sense? So don't listen. So when you start using these symbols, 3 pi over 2, 5 pi over 6, 4 pi over 3, don't lose sight of what that symbol means. It's a number that's still a number of radius lengths swept from the 3 o'clock position. Okay, so that's dividing the circle into fourths. What about into eighths? So if we want 1/8 of the circle, what angle in radians subtends 1/8 of the circle? What? People are saying pi over 4. Right? So 1/4 of the circle is pi over 2. So 1/8 of the circle will be half of that. It'll be pi over 4. Okay, so now we can just walk around and count. We just walk around and count by, every time we do 1/8 of a circle, we're just counting by pi over 4s, right? So 1 pi over 4, 2 pi over 4. Then what's this angle? 3. We're just counting eighths or counting pi over 4s. 1 pi over 4, 2 pi over 4, 3 pi over 4. What's that? 4 pi over 4 is 4. Then what's this? 5 pi over 4. Bottom. 6 pi over 4. Then? Okay. Quick estimate of 7 pi over 4. 5.5, right? Around 5.5. Because it's still a number of radius lengths. Okay, so that's our pi over 4 angles. Any questions on those? So I'm going to, now we can look at the other, so I'll just mark those. Okay, so those are dividing the circles into 1/8 of the circle. Every one of those 1/8 is a pi over 4 angle. Pi over 4. So what if we wanted to divide, say, 1/4 of the circle into thirds? So we're looking at 12ths of the circle. 1/12 of the circle would be what angle? 1/12 of the circle. You just keep pulling degrees out of thin air.
Well, keep
Yeah.
thinking 1/8.
Right, right.
Just goes in
So
like that.
what's so pi over 2 is 1/4 of the circle. So now we want 12ths or 1/3 of that. So it'll be 1/3 of pi over 2. It'll be pi over 6. So if we want to do 12ths of the circle, 1/12 of the circle is an angle pi over 6. About how many radius lengths is that? Remember what that is? About how many radius lengths? It's pi over 6. Quick. So yeah, somewhere about half. We know that's 1. That's 1 radius length, so we're right around a half. Okay, so now we can just, again, we can walk around counting pi over 6. Each time we do that, we're going 1/12 of the circle. Okay, so 1 pi over 6, then 2 pi over 6. 3 pi over 6 is the same as 4 pi over 6. 5 pi over 6. I'm not in the perfect location every time here. What's 6 pi over 6? Pi. 7 pi over 6. 8 pi over 6. 9 pi over 6. 10 pi over 6. 11 pi over 6. Okay, now these, 4 of those can be reduced. So 2 pi over 6 is pi over 3, 4 pi over 6, 8 pi over 6, 5 pi over 6. Okay, so estimate quickly. What is estimate how many radians is 4 pi over 3? 4.1. Find it. So do that. Find 4 pi over 3 and see what that value is. Yeah, 4.19. Which makes sense because a little bit more than exactly 4 radians, right?
But this whole time we haven't found the black marks.
That's what we started with. Those are the whole number radians. That's what we started with.
And you just keep breaking those.
No, see, the whole point is now we're breaking the circle up into nice pieces, which doesn't have anything to do with the whole numbers. We start with pi. So that's exactly 3. Halfway around is our pi, 3.1415, the ugly number, right? Well, ugly because it's not convenient. It goes to an infinite number of decimal places. Okay? All right, so that's where we start. Halfway around is pi. And all these come from that now. We're just splitting up the circle symmetrically based on the number pi. Okay. Anybody have a question? Okay, can I erase this? Okay, so what percent of the circle is, go back to our 1.5 radians. What percent of the circle is 1.5 radians? Find it. Everyone find it on your own. What percent of the circle is 1.5 radians? What'd you say?
23.8%.
Did you get 23.8%? That's what he got. So here's another way to define that angle. So it's the angle whose rays subtend 1.5 radius lengths of arc length, or the angle that subtends 23.8% of the circumference. Okay, so how would you find a percent? If this is your portion, 1.5 is your portion, 1.5 radians is your portion of what whole? 1.5 radians is the portion of what whole in radians? 360 is degrees, right? So what's the whole in radians? 2 pi. Pi is half, so 2 pi is whole. So we want 1.5 divided by 2 pi. That will give us the fraction that this angle is of a whole circle. So this 1.5 radians, 23.8 degrees. So this is a nice way to convert 1.5 radians to degrees. So now find how many degrees that is. Another question? Yeah. How'd you get that?
I found 23%.
Yeah, so now if 1.5 is 23.8% of a whole circle, we want that same percent of what? 360, because that's a whole in degrees. So we're going to take that percent of 360 and tell me what it is again. 80. Someone else get that? 85.9 degrees. Okay, so let's make up our own class angle measure. So this is 1 p.m. 170. What's the name of our angle going to be? We got radians, degrees, gradients. What do we want to do? What's that? Oh no, gradients is already we're making up our own. We're making up our own angle. So here's what's that? ASUs. All right, how many ASUs in a full circle? So we only need to know how to define ASUs. How many ASUs make up a full rotation?
170.
2 people said 170. Okay. All right. Yeah, because we're a 170 class. Awesome. All right. 170. So now I want you to find how many ASUs in 1.5 radians. How many ASUs is the same angle as 1.5 radians? So to get the number of ASUs, what are we going to do?
We'll find the percent as a fraction.
Yeah, we want that same percent of the circle. So 0.238 times 170. We want the same percent of 170 that 1.5 is of a full circle, or 1.5 is of 2 pi. Tell me what it is again?
40.46.
40.5 ASUs. Okay, so now 100 ASUs. How many radians is it? How many degrees is it? Go. 100 ASUs. How many radians? How many degrees? And 100 ASUs. Go. Anybody have a question while you're working on that? Yes?
If, like, you kind of drew an arrow about the path you have to take, is there any way to work backwards? Like, can you find the degrees and then the
Well,
percent of the circle, or do you start by finding your radius?
no, I gave you radians. The reason I gave you radians and I asked you to find degrees. So that's why you would do that path. If I gave you degrees and you wanted radians, then you'd go the other way. But it was just, yeah, I gave radians first. Any other questions? Okay, so now we're doing 170. I'm guessing something like that. Am I right? Kinda? Further? Or
That's about right. Anything further.
What'd you do first? Okay, what percent of the circle? So we got 100 ASUs? And what percent of the circle did you get? 58.8%. Nice. And so now we can easily get degrees and radians. To get degrees, we take 58.8% of 360, and we get 211.8 degrees. And then we take 58.8 degrees of, or percent of, 2 pi. And we get
3.695.
3.7 radians.
How did you get 158.8% out of 100 ASUs?
So if you want to know what percent 100 is, how do you get the percent that 100 is? What's a full rotation of ASUs? No, that's radians. We said 170, right? 170 is a full rotation. So how do you get the percent that 100 is of 170? What'd you do? Divide. So you got 100 over 170. Should give you that 50.588 number.
It's quickly, and I don't know.
Yeah, so it's just a matter of percent. It's just a matter of percent. So maybe you just have to review that. But I mean, think of this. Remember our decay factors, right? What happens when you multiply a number by 0.588? Right? This is like a decay factor. You're keeping what? You're keeping 58.8% of it, right? You're losing, your percent decrease is 41.2. And you're keeping 58.8. So you're multiplying by 0.588. You keep that fraction of it, or 58.8% of it. Okay, any other questions?
How'd you get to the degrees of the radians again?
Ask me again?
Oh, no. I see how you got to 211.8 degrees, but what was the formula to get to the 3.7 radians?
Okay, so it's all about percent of the circle. So we want the same percent of the circle in radians that all these others are. So we want 58.8% of what?
360?
No, radians. There's not 360 radians in a circle. So how many total radians in a full circle?
6, right? Or 6.2 pi.
exactly 2 pi. So we want 58.8% of 2 pi. Got it? Yeah. Yeah, so all you have to know is percent and then how many total you have in each of these things. Okay, other questions? All right, so let's go to worksheet. Is it worksheet 2 or 3? What is this? Worksheet 3, page 273. Okay, so it says imagine a bug sitting on the end of a fan blade, and the fan blade rotates in the counterclockwise direction. The bug is 2.6 feet from the center of the fan and is located at the 3 o'clock position when the blade begins to turn. So this is the starting point. Like we said, that's our convention. The starting value is the 3 o'clock position. And so we're just going to assume that the bug is at the very tip of the fan blade, the very end. And so the radius of our fan blade is 2.6 feet. And then the fan starts to turn. And the bug holds on for dear life, because it wants us to help us succeed in this problem. Okay? So it's just going to go around and around. So let's do some practice review problems here. We'll start on number 2. So number 2 says, if the bug travels 5.2 feet, first of all, let's draw the circle here. Can you see the circle? Yeah. So if the bug travels along the arc, if it travels 2.6 feet, something like that. Did I say it right? 5.2? If the bug travels 5.2 feet, then what angle measure in radians did the fan turn or sweep out? So if we understand radians, that should be a pretty easy question. So here the bug goes 5.2 feet along the arc. And we're asking, how many radians did the fan turn? Let's see where to put this. There we go. Okay. So if this is 5.2 feet of arc length, and the radius is 2.6, then what angle did the fan turn? Some people are saying 2 radians. So the number of radians is the same as the number of that openness of that angle is the same as the number of what? Radians is the same as the number of radius lengths subtended by the angle. That's where radians comes from. It comes from the number of radius lengths subtended by the angle. So if each radius is 2.6 feet and we went 5.2 feet, how many radius lengths did we go? 2. Okay, then the next question is 11.7 feet. So 11.7 feet, something like down here now. So I'll do that in red. Okay, so now 11.7 feet. How would you find out how many radius lengths that is? Yeah, you're going to take that and chop it up into equal lengths of 2.6 feet and see how many of them you have. You're asking how many radius lengths fit into 11.7 feet. And you get 4.5. So 11.7 feet is our total arc length. 2.6 feet is the radius. And this gives us the number of radius lengths. That should make sense. The total arc length, chop it up into equal pieces of the length of the radius. That ratio then will give you how many pieces you have, how many radius lengths. And then we know that that number of radius lengths is the same as the number of radians. Okay, so that's where we get theta equals S over R. Okay, do number 3. So, on your own, do number 3. They're at the bottom of the page. But think about what makes sense. Don't try to use a formula. Just think about what makes sense. Okay, so 0.765 radians. So without doing any calculations, we should have just kind of a general idea of what that's talking about. The fan is going to turn 0.765 radians. About how far will it turn?
A little more than 1.3 feet.
Okay, but you're talking in terms of feet. I'm talking about how much of a rotation should I
A
do?
little over 3/4 of a radian.
Okay, and what's that?
1.989 radians.
You guys you're talking about calculations. I'm not talking about calculations. I'm thinking 0.675 radians. You said a little more than 3/4 of a radian. Good. Okay, so what's 3/4 of a radian? What's that about?
3/4 of 2.65 feet.
Yeah. So it's like 3/4 of a radius length. So here's our radius length. So it's going to be an arc length that's about. Tell me when to stop. Yeah, about 3/4 of that. Okay, something like that. So now I want to get exactly how far did the bug travel. So if that's the number of radius lengths, and each radius length is 2.6, how would we get exactly how far? So we went this this fraction of one of those. Oh, multiply, right? Multiply. So we want 0.765 of 2.6. And many of you were saying, what is that? How many feet is that?
1.98.
About 1.99 feet. Okay, pi over 2. Where will turning the fan pi over 2 radians, where will it put the bug? Halfway around. So pi over 2 will put the bug here.
No. Quarter.
Quarter of the way. Right about there. So this is pi over 2, an angle of pi over 2, which is pi over 2 radius lengths. And each radius length is 2.6 feet. So we have this many of those gives how many total feet? Okay, so here we're looking at how many radius lengths times the length of each radius will give you total arc length in feet. Okay, so how many radius lengths you go times the length of one radius length will give you then the total distance in whatever unit that is, right? In this case, feet. Okay, questions on those? Let's kind of review. So now going back to question 1, our goal here is to track the location of the bug as this fan turns. So be able to track exactly what the location of the bug is as it turns. So what quantities might be involved in that? What's that? Okay, the radius. Is that a changing or constant quantity? That's constant. That's our 2.6. What other quantities will help us track the position of the bug? Arc length. So, arc length from where? From 3 o'clock in? Arc length isn't in radians. So we could do it in feet. Okay? Arc length from 3 o'clock position in feet. That we can monitor the position with that. What else? What distance? Like straight line distance? So isn't that what we just did? What's that? What is 2 pi? Okay, C, circumference of the circle. Fixed or changing? Okay, here, let me give you an idea. So what if I threw this thing up here, which we call the horizontal diameter? So how could that help us, the horizontal diameter, in tracking the position of the bug? What new quantity could we talk about using the horizontal diameter? What's that? Yeah, but what quantity of the bug are we talking about? What's that? How many radians past the halfway mark? How many feet?
Like using pi being halfway around
Mhm.
the circle, you could use pi to find how many feet from halfway.
So it's another arc length, still arc length? Okay. All right, what about if I add this to the picture? What is that showing? Yeah, so vertical distance from the horizontal diameter. Okay, similarly, what else could we do? Yeah, so we could have what's called the vertical diameter. And we could monitor what? Yeah, the horizontal distance. Now, in this vertical distance, I should have said the horizontal distance, not from, but above. I should have said above. And going back to that, why does that work? Is it always above? No, half the time it's below, right? So what's the meaning of this quantity if half the time it's above, half the time it's below, and we define it as the vertical distance above? Okay, so positive and negative, does that make sense? So when it's below, those values will be negative. And when it's above, it'll be positive. So if you're -3 above something, you're 3 below it, right? If you're -3 above, then you're just 3 below, okay? So that's why that works. So going back to our horizontal distance, how are we going to define the horizontal distance what are we going to say? Horizontal distance to the right. We want positive to be to the right. Of the vertical diameter. So would you agree if we tracked both of those, the vertical distance and the horizontal distance? So the vertical distance above the horizontal diameter and the horizontal distance to the right of the vertical diameter, we could pinpoint the exact location of the bug for any angle or any arc length. Okay, well, if this was just our axes, right? If these were like axes, and that was the origin, the center of the fan, what is this really talking about? The vertical distance above the horizontal diameter, or this right here. Vertical distance above the horizontal diameter. It's the y value. You had the right idea, just spoke a little too soon. Okay, that's the y value, okay? And what is the horizontal distance to the right of the vertical diameter? Right now, what's x like? Negative, right? And that's why it's because it's to the left. When x is to the right, we know it's positive. To the right of the y-axis. When it's to the left of the y-axis, it's negative. So the functions we're going to be working on are their input is going to be theta, the angle. We never said that as a quantity. So theta is the angle swept counterclockwise from 3 o'clock position in yeah, it could be in anything, okay, but we're going to do radians. And we'll explain that later, why it's going to be radians. Okay? And then the output we're going to have two, so it's going to be two different functions. The horizontal distance to the right of the vertical diameter will be 1. And then we'll have a new function whose input is the angle swept counterclockwise and whose output is the vertical distance from the horizontal diameter. And so by monitoring those two functions for any given angle, those two functions will output the exact position of the bug.
Did you have 4, like x to the right, x to the left, y to the right?
But so if the vertical distance above is 2, then how can we use that same function to show us what below is? How can we use it? What would that value be? Negative, right? Just like a y-coordinate. So we only need 2. Okay, written homework for Wednesday. See you then.